Oh, my voice is audible.
Yes, sir.
Okay. My 36 participants. Okay, today we'll start digital image processing second model regarding the image transforms. In first model, we studied the basic fundamental steps in digital image processing. What are the components we require to enhance or to compress, to do some modifications on image, and we have seen operations of an image, and we have seen relation between the pixels, and last we have seen image geometry also we have seen. right? And second module, we are going to see the transformation techniques which we are implementing on any images.
నీది జాయిన్ అయ్యా నాది జాయిన్ అవ్వాలి నీది జాయిన్ అవ్వాలా చరణ్
So first we'll see the need of transforms. Why we need what is an image transform. If you observe, so consider an image with an n by n matrix. See, already I informed that image we are going to implement in terms of matrices. So 2 by 3 matrix, whether it be a square matrix or rectangle matrix or whatever matrix it may be, right? Maybe a square matrix if any n matrix. If it is not square matrix, rectangle matrix, m by n matrix, right? Here, so the importance of the transform or what is image transform means. So consider this is an original image which you want to get as an input of your camera. If you apply some transformation techniques on this image, so we are going to expect another image which is having of same size. That means n by n matrix, if we transform, we are going to expect the same n by n matrix, right? So this is another image. So this is, we can call as a coefficient matrix, right? If you take another time the transformation, that is inverse transform, then you are going to get back the original image. So you may ask doubt, what is the use of transforming? Again, what is the use of inverse transforming? This is exactly what we are expecting for communication. That is a modulation and demodulation. I don't want to describe again what is modulation, what is demodulation. I think you are aware of the modulation, need for modulation before transmission, and after transmission, after receiving, demodulation to get back the original modulating signal. So similarly, initially we are going to transform image into another format, but the size will be same size. And after that, we are going to take back the inverse Fourier transform and to get the original image. So already in digital signal processing, we have seen Fourier transform, discrete Fourier transform. We need to observe for digital image processing, right? So we are also go for a fast Fourier transform for the images also. So where computation will be very fast during fast Fourier transform. So that is the image transform, right? So next, if you see applying transform, we get another image of same size. After applying the inverse Fourier transform, we get the original image back. What I explained just now. Then what is the use of image transformation? The question again. So what is the use of this image transformation? So to enhance or to resize. So whatever the application you need, based on your requirement, we need to use the transform. Which transformation we need to use? So we are going to see that which transformation is suitable for the concerned image for your requirement in the second module itself. So what is the application of this image transformation is pre-processing. So pre-processing need filtering and enhancement. In pre-processing concept, we are going to see the filtering and enhancement. If you want to separate applications, you can directly go for filtering, enhancement, data compression, edge detection, corner detection. But how we are going to segregate that applications? So based on pre-processing, based on data compression, and based on feature extraction. Then in pre-processing, what are the applications we can get means filtering, enhancement. These are the two concepts we can go with. So next is data compression. So data compression is resizing. So we are going to use so many transformation techniques to compress the data. Right, normally if you want to send one file which is big file, more than 25 MB, if you to other person, so directly through mail it will not send. So what we are doing, we are going to create a RAR file, or we are going to make it into zip file. So then we are sending. So it will be very easy. So data will be compressed, but there is no loss of information in that. So be cautious that when we are compressing the data, we are not going to lose any single bit of information. So like that, we need to compress the data, right? For example, if you take one image, open in the paint, if you resize, what happens? Definitely, the after resizing, the image may not be as that of original image. So may not be that much clear as earlier. So some disturbance, some blur occur in that image. So then we can expect that some loss of information is there in that. But in data compression, which we are going to follow the techniques, so there will be no loss in any information. Just the size will decrease, right? So that's the concept we are going to implement in data compression. So discrete for cosine transform is there. So wavelet transforms are there. Some transforms are there where we cannot get disturbance while compressing the data. That means original data as it is, it will be get, but there is no loss of information. Like zip file. So are you going to lose any information if you made a zip file or RAW file? for your concerned input of the file. At the end, the receiver also will put the same file. You need to unzip the file to get the picture or to get that data. But the loss of information is zero. But the concept is for communication purpose, for transmission purpose, we are making use of the techniques, zip or raw file, and we are transforming. Again, at the receiver side, receiver has to unzip that file and get back the information back. So this is a process. So these are transmissions required in each and everywhere, either video transmission or audio transmission or whatever thing is there. Just we are going to make some transformations and then we can get back after receiving the same information by the end. Right? So there's the importance of transformations, right? So next, the third feature is application is feature extraction. So edge detection and corner detection. So can you make the difference between edge and corner? So by understanding, unknown person can easily identify that both are same. Edge and corners both are same. But as a professional student, as a digital image processing learner, we should not say that edge and corner both are same. Both are different. So how both edge and corners will different? So we'll see one example based on this, right? So next, what is the image transform? So initially we learned what is meant by transform, right? What are the applications of transform? Next, what does the image transform do? So that it represents the given image as a series summation of a set of unitary matrices. So we are going to make use of the identity matrix, that is unitary matrix. So where if you multiply any matrix with unitary matrix, the output will be remains same, right? So A into I equal to A itself. So that is identity matrix or unitary matrix. So what is unitary matrix means? If you see here, if matrix A is a unitary matrix, if its inverse is equal to the transpose, that means we can also go for a conjugate of A. So this is called as a conjugate. The star indicates where A star is the conjugate of A. Right? Now we'll see some basic unitary matrix functions. See this, an arbitrary continuous signal x of t can be represented by a series summation of set of orthogonal basic functions. Right? So in matrices, we are going to deal this x of t. So where this t stands for time domain signal, there is a continuous signal we are expecting. Right? So it is represented a series summation of set of orthogonal basic functions. So what are orthogonal basic functions? There will be some formulas in mathematics. Of course, these PPTs are not related in our syllabus, but it is important to discuss about the importance of transformations in second module. So that is, if you want, you can go for history of the second module, so which is important to understand better the second module. This x of t equal to summation. So Cn an of t, there is an infinite series expansion. We can go where n equal to 0 to infinite, we can expect, right? Can start from 0, right? So whereas here, this x star of t equals summation n equals 0 to n minus 1, Cn an of t. So we cannot say that this is an infinite, but where this n values may be infinite, this small n values may be infinite, but that n values are restricted up to n minus 1, right? That capital N value, we will define the number of pixels or number of size of the picture, size of the matrix. So this n may be infinite, but this n we are restricting at n minus 1 itself, right? So in a discrete signals, so we have a series of one-dimensional sequence. Say for example, in digital signal processing, we have seen only one-dimensional Fourier transform. We are not mentioned two-dimensional. For example, if you go for Fourier transform of x of n, x of n is equal to there is a input signal, if you consider f of k. Hello? 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 Somebody say something. I can put in chat box also, no problem. My voice is audible. Hello?
लीला होते हैं मौसम को काम न करना देकर उठा Hey.
421, please mute yourself.
కమలకాండ దగ్గరికి కట్ట తీసుకో అఖిల్ కూడా పో దాన్ని కొట్టిరా పండి ఇద్దరు అఖిల్ ఇద్దరు పోండి అన్న కొట్టిరండి.
Hello, my voice is audible to you. Who is scratching on the screen? Hello. See. So this is, we can expect one-dimensional signal. So after expansion, if you see this previous one, we have series of one-dimensional sequence of samples represented by E of n 0 less than n minus 1. So we have n number of samples, so we represent this set by the vector u of dimension n, right? So we are going to define the image in terms of u and v for a corresponding x and y variables, right? So where v is a transformed vector and a is a transformed matrix for a given n by n matrix, right? So we multiply this. Expansion v of k for summation equals 0 to n minus k, k of n, k comma n, v of n, where k value stands for 0 to n minus 1. So a of a comma n is a matrix format we can expand. So 0, 0, 0, 1, 0 to the first row itself is 0 row, next one first row, second, third up to k rows. So this explanation of that v of k is a two-dimensional one. So two-dimensional signal we can expect. This is a two-dimensional one. Right? So in the two dimension, we are going to expect both the m and n. So where k and l are represented to maintain the sequence. So that's why n square unitary matrices we are going to get. If it is m by n matrices. If it is n by n square default. So these are two-dimensional matrices we can expect. So u will be like this. See 421, please unmute yourself. Lot of disturbances coming from your device. See, I came to know that the concerned student cannot get login, but one of your friend login in two devices with different roll numbers. Same person login with different roll numbers. In future, I don't want to expect such type of things, right? Understood? So only one person login twice with a different roll number and different devices. So please inform the concerned those who are absent or those who are proud to make like this, right? Please don't do like that. See, attendance is not mandatory to give your marks. There is a period based on your performance itself, right? And I am not expecting that you are going to learn everything from the teachers itself. As a final student, you are very much familiar what to do, what not to do. But this type of tricks, please don't try to play. Please avoid such type of situations, right? So honestly, join yourself only. If you are not willing to work, you are not willing to log in, please no need to work, right? So your friend, one of your friend, are using two mobile phones. In one mobile, his or her roll number. In another mobile, another device, his or her friend's roll number. So please don't do like that. So this is the introduction part of your second module. So for example, if you see this is your two-dimensional Fourier transform. The first topic in your second module is two-dimensional Fourier transform of a continuous signal f of x comma y is given by f of u of e. This is a Fourier transform. So integral minus simply both the double integral will be there. Why? Because we have two-dimensional thing. So dx into dy. So e power minus 2 pi. Actually, in digital signal processing, please remember the concept of Fourier transform and discrete Fourier transform. So in Fourier transform, so for x of n is the input signal, then x of k is the Fourier transform of that x of n. But x of k is integral x of n. So e power minus j 2 pi n k by 2, right? So that is your one-dimensional thing. So in two-dimensional, this is your original picture image f of x comma y e power minus j 2 pi ux plus vy dx comma dy. So dx into dy. So sometimes once you go with the differentiation with respect to x, and another time we need to go for differentiation with respect to y. This is a two-dimensional image Fourier transform. So what is its inverse Fourier transform? So its inverse Fourier transform is this one: f of x comma y equal integral minus to infinity f of u comma y. That is a capital one. Then e power instead of minus we are going to get plus. So j 2 pi ux plus vy dx dy. So in digital signal processing for one dimension we have seen that 1 by n or 1 by 2 pi we have seen, right? So whereas here f of u comma v is r square uv plus after differentiating we are going to get this one, so Fourier transform of f of x comma y, and we are going to express the phase angle for this. So phase angle is the tan inverse I. I stands for illumination u comma v by r stands for reflection u comma v. So is the phase angle for that, right? So p is the power. So how much power we can expect for that image is represented as f of uv. There is a modulus f of uv whole square, and that is nothing but already defined what is f of u comma v, r square u comma v plus I square u comma v. This is the power spectrum for that. So please unmute yourself and respond to your roll numbers. I'm going to take attendance. Please unmute yourself. So 462,
Present sir, 462.
63,
Present, sir.
Sir,
64,
62 present sir.
okay, 64,
464 present, sir.
65,
Present sir.
464
66,
present.
66, 67,
Present, sir. 67, present,
68,
sir.
Present, sir.
69,
Present, sir.
70,
Present, sir. Present, sir.
71, 71, 72, 73, 74, 75, 76,
75, sir.
huh?
76, sir.
77, 78, 79,
Present, sir.
80,
Sir, 74 present, sir.
okay, 80, 81,
81 present.
82,
Present, sir.
83,
Present, sir.
84,
Present, sir.
85, 86,
Present, sir. Present, sir.
87,
Present, sir. It is on.
88,
Present, sir.
89, 90, 91,
Present sir.
92, 93,
Sir, 91 present sir.
okay sir, 93, 94, 94, 95,
Present, sir.
96,
Yes, sir. Present.
96, 97, 98, 99, A0,
Present, sir. 99.
A0,
Present, sir.
A1,
Present, sir.
A2,
Present, sir.
A3, A4,
Present, sir.
A5, A6, A7, A8,
Yes, sir.
A9,
Present, sir.
B0, B1,
Present, sir.
B2,
Yes,
Hello,
sir.
sir. B not
B3.
not present, sir.
B3 present, sir.
Sir,
B4.
B not present.
Okay, B4.
Present,
B5.
present, sir.
B5. B6.
Present, sir.
B7. B8. B9. Neeraj.
Present, sir.
C0.
Present, sir.
C0. L13.
Present, sir.
14.
Present, sir.
15.
Present, sir.
16.
16 present, sir.
17.
Present, sir.
18. 19.
Present, sir.
20. 21.
Present, sir.
22.
Present, sir.
23.
Present, sir.
24. 24.
Present, sir.
Next, Abhishek. 427.
present, sir.
Okay, okay. 427 Abhishek.
Sir.
And 4F3. 4D8. And 408. See, option is
Sir,
466.
present, sir.
Okay. First listen after this. 66.
4B not
71.
present.
See, first I am going to announce the option list, please. Let me go with that. 66, 71, 72, 73, 77, 78, 80, 89, 90, 92, 94, 96, 97, A3, A5, A6, A7, B5, B7, B8, C0, L20, and we didn't get 4F3, D8, and 408. Right?
23 present.
823 present, Master. Oh. I said 820.
427.
427 present, Abhishek.
Okay.
I explain, please don't use two devices in order to protect your friends' attendance. So please let them attend it themselves. Please don't do like that. Right? So next class, day after tomorrow, we'll start again this second chapter. So due to my internet connectivity also, it's full. So we can attend next class now. So please, you can leave this class.